The Boeing 777's journey from design to reality faced its most critical phase during testing. This was the moment when every system, component, and innovation underwent rigorous scrutiny to ensure the aircraft met the highest standards of safety and performance. From overcoming pressurization challenges to perfecting engine reliability, hunting for crosswinds, and conducting high-speed taxi tests, the 777's development was marked by relentless determination and ingenuity. This video delves into the obstacles, breakthroughs, and teamwork that defined the testing phase, leading up to the aircraft's historic first rollout.
In the frigid depths of an Alaskan winter, a single component of a new airplane undergoes testing. It's a fuel-related part, largely unknown to most, yet vital to the aircraft's operation. Known as an Auxiliary Power Unit, or APU, it serves as an emergency generator, providing electrical power if one or more engines fail. Engineers from the company developing the APU have traveled 2,500 miles from their homes in Phoenix, Arizona, where temperatures are about 50 degrees Fahrenheit.
That's my end, and I'll see you. Hey, take.
At any hour, day, or night, Vince Carroll may be called to oversee an engine startup. These startups, triggered randomly by computer, are mandated by the Federal Aviation Administration to ensure the APU starts reliably in extreme weather conditions. To simulate such conditions, the APU is cooled to Alaskan temperatures that sometimes plunge to 59 degrees below zero, with water liberally sprayed over its components. Over 6 months, the computer has initiated over 500 engine startups. To date, none have failed. The rigorous Alaska testing is just one small part of Boeing's efforts to design and build a new aircraft, the 777. Designed using computers and constructed from the latest lightweight materials, the plane will be powered by 2 of the world's largest jet engines. If Boeing's predictions are accurate, the 777 will lead a new generation of aircraft designed to meet the evolving air travel demands of the next century. With no signs of halting production, a recent downturn in global aviation has caused canceled orders and workforce reductions. Shifting travel patterns have led airlines to seek slightly smaller planes capable of flying longer routes. The 777 is Boeing's answer to this demand. Viewed by many as a pivotal project, its success is crucial for the company to compete with Airbus and McDonnell Douglas. However, the development hasn't been inexpensive. While Boeing has not disclosed the exact costs, estimates suggest they will surpass $5 billion. Based on a commitment made to customers years before the 777's existence, Boeing has already sold 147 units at an average price of over $100 million each. This promise guarantees that new design, manufacturing, and testing techniques will deliver a plane ready for immediate service, avoiding the typical year or 2 of teething issues experienced by some earlier airliners. The head of the 777 project, Alan Mulally, has dedicated the past 6 years to this aircraft, vowing to achieve what many deem impossible, creating a plane safer and more reliable than any in aviation history. If he succeeds, much of the credit will go to a novel management approach called working together. Despite its unassuming name, this principle is revolutionary in the aircraft industry, aiming to eliminate secrecy and rivalry within the company, and even in relationships with some external partners, such as customers and contractors. The 10,000 people working on the 777 are adapting to this bold and sometimes uncomfortable shift from traditional practices.
I think the human spirit is a fabulous thing. And I think there are beautiful butterflies in all of us. And I think that we come with no baggage and no burdens and no limitations in our own minds. And I think the environment we're trying to create is that we'd have a shared thought, a shared vision, a shared appreciation, a shared understanding of what it is we're really going to try to accomplish together. Ready, Andy? Go.
We're going to work problems and not avoid them. Say it. Come here.
Say it loudly.
We're going to work all our problems, not avoid
And
them.
no secrets, right? Because you can't work a secret.
Mullally conveys this philosophy with infectious enthusiasm, though not everyone found it easy to shed egos and openly discuss problems at the project's outset.
An engineer with pride wants to find the solution to his problems. And it's not a natural thing to go out and explore publicly the particular problems you have. You'd like to do it and be able to handle those yourself. So I'd say, yeah, there was resistance at first. And I think over the years, that's gone away. I think we kind of shouted from the rooftops in our program reviews with large audiences. In our all-team meetings, it's been said. The same words have been used. It's okay. It's almost like celebrate our problems, get them out in the open so we can go work them.
Traditionally, challenges in aviation are tackled through relentless testing. All new aircraft must undergo rigorous safety and durability evaluations. But Boeing insists the 777 will set a new benchmark as the most thoroughly tested plane in aviation history. From the structural integrity of individual components to the operation of flight controls, the reliability of electronics, and the performance of the entire system, every aspect will be tested and retested. Components like this passenger door are tested under the harshest conditions they might encounter during service. Boeing has constructed vast new test facilities specifically for the 777, running flight simulations long before the complete aircraft was assembled. With 6 months remaining until the scheduled first flight, the test program reached a critical milestone.
Okay, I just had a religious experience. Guess where I've been?
The airplane?
The airplane. And it really happened yesterday. Engineering and operations allowed me to turn on electrical power. And I did it just like the airlines would do it. I went up to the side of the airplane and made sure the big power feeders from ground power were hooked in, that all the lights were on. The polarity was correct. And then I went up to the cockpit and I pushed the battery switch, and then I pushed primary power, and then I pushed secondary power. And all the lights in the house came on.
Oh, I think great.
4.5 years after we laid out the program, we turned on electrical power, all the wiring's in, it all works, all the voltages moved to the right places, on schedule 4.5 years later. Isn't that something?
This will be the first 777 to take to the skies. 6 other planes, identical to it, are being assembled in a mile-long production building. However, at present, this aircraft is missing 2 vital components: its engines. The 777 is a twin-engine aircraft, like 85% of the planes currently crossing the North Atlantic. Engine manufacturers are racing against time to meet the schedule, despite last-minute design adjustments prompted by 6 months of rigorous testing. Since the introduction of the four-engine 747, all subsequent Boeing models, including the 757, have featured 2 engines. For the 777, engines will come from Pratt & Whitney, General Electric, or Rolls-Royce. Twin-engine planes make economic sense for manufacturers today. These engines, accounting for 20% of the plane's total cost, are complex and expensive. However, some pilots, less persuaded by economic arguments and more concerned with safety, still believe that more engines equate to better safety.
Hello, Jeff Peace. How can I help you? This is Lee Marvin, yeah.
One Boeing executive, Granville Fraser, a propulsion engineer, provides insight into these debates.
First of all, engines cost a lot of money, and engines require maintenance. More engines cost more money. So our data shows that better economics, which is a very strong driver in the airline success, comes from having fewer engines. Now let's go back and look at the other aspect of it. If the engines were 100% reliable, then it doesn't make any difference, because if they always run, then having extra engines just means you've added expense and maintenance and overhaul work you have to do for no value to the airlines. People who look and say, the only reason why I only have 4 on my airplane is because I don't have room for 5, is a guy who's thinking about maybe the reliability of engines from the earlier time periods.
Today, manufacturers work to prevent in-flight engine shutdowns by eliminating even minor issues, such as faulty warning lights or loose oil caps, from engine designs.
The Boeing company led an effort to go through in excruciating detail every single incident that had occurred where an airplane had to deviate from its intended flight path. And an interesting statistic is that over 50% of all of the engine shutdowns in the world in commercial aviation have nothing to do with a core engine. They have to do with pneumatic systems or electrical systems or fire detection systems vibrating, and so right out of the analysis came a very obvious an issue, and that is that if we could improve their reliability, then you could assure the airlines that they could fly for long periods of time over water up to 180 minutes.
The importance of 180 minutes is tied to a set of regulations called ETOPS, Extended Twin Engine Operations. These safety and reliability standards apply to all twin-engine aircraft and have been a key focus for the 777 development team.
ETOPS, the first gate we have is gate 2.
Airlines must obtain approval from regulatory bodies like the FAA in the United States and the JAA in Europe to operate twin-engine planes more than an hour from a suitable airport. This approval, required in case of an engine failure necessitating an emergency landing, is typically granted only after a new model demonstrates reliable performance for at least a year. Under the 1-hour rule, vast areas of the globe are off-limits to twin-engine aircraft, as shown in the dark blue regions on the map. The 2-hour rule offers better flexibility, though portions of the Pacific remain inaccessible. However, if twin-engine planes can extend to 3 hours from the nearest airport, virtually the entire world becomes accessible. To some at Boeing, the 1-hour ETOPS rule feels outdated.
The original rule in the United States was drafted in 1953, the 1-hour restriction. And that rule was based upon the reliability of the piston engine airplane. The broad spectrum of today's airplanes, and not just ETOPS airplanes, has engines that are at least 10 times more reliable than those engines, and an accident rate related to engines that's at least 60 times better. What one worries about is the dual unrelated failure. In other words, one engine fails and 30 minutes later another engine fails. In the entire history of the Western-built jet transport fleet, from 1959 through today, we have never had a dual unrelated engine failure on a twin-engine airplane, in spite of much higher shutdown rates that engines had prior to the advent of ETOPS.
Although European regulators denied the 777 a 3-hour ETOPS rating, Alan Mullally remained hopeful about future approval.
Of it as a surprise as such, because we've been talking to them all the way along about the plan, and we know the people involved, and we know how they feel, and we know what their experience is and in this area, and so we're really, I think overall, I think we all feel very good about making progress on getting to the place where airplanes don't have time limits on where they can fly.
In late 1993, an iconic aircraft, the very first 747, was leased from a museum and fitted with a Pratt & Whitney 777 engine in place of one of its 4 smaller engines. This modified 747, known as a flying testbed, will test the engine's performance in flight after extensive ground testing.
You need to fling one about the sky and have the rotors and the case work their clearances out, and you need to see how the engine is going to operate when you're pulling a rapid wind-up turn or an avoidance maneuver. With air loads on the fan case, pulling it towards the tips of the fan. So in the past, we have always, brainstorming, decided you should go have a flying test bed and take the engine up and fling it around the sky. Well, our design techniques and our test techniques and the facilities that are available to test in simulated facilities are becoming better and better and better.
Pratt & Whitney operates an advanced testing facility in Tullahoma, Tennessee, equipped with low-pressure altitude chambers and wind tunnels. These facilities simulate both normal and abnormal flight conditions, allowing jet engines to run at full thrust. For instance, engines must withstand the rare but serious event of a fan blade detaching mid-flight. A synthetic fiber shield is installed to prevent the blade from piercing the engine casing. Engines are also tested against severe environmental challenges, including large chunks of ice, torrential rain equivalent to a 28-inch-per-hour storm, and even bird strikes. Bird ingestion has caused crashes in the past, so engineers launch dead birds at the engine, progressing to specimens weighing up to 8 pounds. Despite the thoroughness of ground tests, a lingering question remains. Can ground testing fully replace the insights gained from actual flight testing? Over recent years, debate has grown within Boeing and among engine manufacturers about the necessity of a flying testbed. Could some of the more intricate engine tests simply wait until the plane itself was complete? One key consideration is cost. Ground testing is significantly cheaper, though some Boeing engineers felt the added expense of a flying testbed was justified.
If Boeing and Pratt or any engine manufacturer decided to split the cost like they've always done in the past, nobody would be arguing about this one. And the thing you're missing is you can get the altitude facility, you can get the sea level static facility, you can get the operating lines, you can get everything, but you're never going to get what that 27-degree angle of attack rotation puts a distortion into the fan blade. Does it get a mode of flutter, which we don't know? It's not going to get the case deflection. It's not going to get the strut-wing interaction.
John Cashman, the chief test pilot for the 777, strongly supports testing engines both in the air and on the ground.
The more interesting testing is where you're doing the outside corners of the envelope, so to speak. because you're loading the engine to very high power and taking it to very critical airflow angles to the inlet. And at that point, it's somewhat unknown exactly what it will do. The air engine has never been there before. In putting that in a ground simulation, they do work to simulate it, but they can't quite get it the same as you can in flight. And the events that can happen when the airflow separates off the front of the engine and goes into the engine can make the engine be very unhappy. It can bang and what we call surging, where the blades of the engine basically separate and the engine fires forward.
I would, from my own standpoint, have been ready to make the decision to go to the Tullahoma tunnel without the back-to-back test on the airplane. There were people who were not willing to do that. Those people happened to be in a position to make the final decision, and I wasn't.
In contrast, Ron Ostrowski, the 777 Director of Engineering, was more inclined to rely solely on laboratory testing.
To be quite honest with you, I recommended we did. I recommended we were ready to do that. Now, in hindsight, I had a lot of advice from others, and it was good advice.
You know, we all listened and we all talked about it, and we decided, well, you know, it's a big development program, and it's a big change, and so why don't we go check it out on the airplane, and then we'll validate that correlation between the ground facility and the flight test. And then if it turns out that it really is, we really do understand it from the ground facility, then we won't fly subsequent engines, you know, on flying test beds. So I think it'll both people will be right, kind of, and we'll learn a little bit, but I think most of the knowledge we'll have known, you know, from the ground testing.
The Flying Testbed program launched in November 1993, and on the third flight, Cashman's concerns about a potential engine surge proved prophetic.
It's a very large explosion that you hear. It's like a shotgun going off. Usually there's a motion in the airplane where the airplane will turn slightly into the engine that surges. I think after the second surge, the crew pulled the engine back to idle, and it surged, I think, in the process of that, and then it stabilized. They did not shut the engine down. It recovered on its own.
It's kind of like an engine backfiring. And which was a gift, which was good news. It was a good piece of data. And following analysis of the engine and looking at the test data we gathered, we realized that the case that surrounds the fan blades needed to be a little stiffer because it was moving a little bit more than what we had in the design. And that allowed a little bit too much clearance between the tip of the fan blades and the case, which allowed the fan blades to stall, just like an airfoil. So it was just stalling. It was at a stall point because it had a little bit too much space.
For Mullally and his team, an issue encountered during this phase is seen as an opportunity to prevent more serious problems later. The surge led to several weeks of intensive work, focusing on redesigning the engine's compressor case.
So I think it's a perfect example of include all the lessons learned, do the best design you can, but then comprehensively test it on the ground, in the test facilities, then comprehensively test on the airplane, and learn from the data, and then be able to deliver an even better quality engine. I think Pratt is really pleased with the engine now, and I think the airlines feel real good about it, and I know that we, the Boeing company, feel real good about the quality of the Pratt engine now, and we feel really good that we went through this design and validation program together.
We had not tested for that specific condition at the point we flew on the 747. It was part of our program to do later, but we had not accomplished that specific test condition with an engine that had the configuration that we were flying. and we got a surprise. We learned something. And if you don't learn, particularly if you don't learn and file it away for the future, then you're not doing your job. And we did learn something. And we've accommodated it both in the way we test and also in our configuration.
Ultimately, the debate over the necessity of a flying test bed boils down to finely balanced arguments. The ground tests had revealed the surge when the engine was later evaluated under conditions identical to the third takeoff. However, the situation was complicated by the fact that the test engine had endured significant wear during earlier ground testing. Eventually, the engine design passed the critical evaluations necessary for certification on the 777. Examining a single test highlights the complexity and frustration involved, as engineers verify whether their theoretical calculations match real-world performance. For instance, planes sometimes must taxi and take off in crosswinds, strong winds blowing across the engine inlet. If the design isn't optimal, the airflow can become turbulent and separate, reducing efficiency. The most effective way to test this is under actual crosswind conditions when they can be found. In November 1993, just before Thanksgiving, the flight test team convened to determine if any location in the United States had sufficiently strong winds for this specific test.
Some of the weather data they're predicting tomorrow is when they really expect the winds to hit. They're expecting 15 to 25 miles per hour, which translates into the low 20 knots. I guess as much as you can nail down a meteorologist, they have a fairly high confidence that there's going to be the predicted winds tomorrow. The question is it close enough to make it worth launching and expending all of the effort and budget to go based on those forecast winds?
I mean, that's the nature of this, isn't it? It's a turkey shoot, and we got so many windows of opportunity. I'm inclined to believe we go for it, but
Wasn't there estimates that the winds were likely to peak tomorrow afternoon?
Yeah.
So we could be in place in time to support that
If we left tomorrow morning. I think, Brad.
Well, it's the last shot before the holiday. That's what do it, huh? Well, what else are you going to do tonight?
The next morning, a flight crew and engineers boarded the plane to go crosswind hunting.
Personally, from a gut feel, I would put it at 50% at best. If the weather does come through as predicted, and we can get over 20-knot winds, then hopefully we can get inlet separation. You know, the goal is to have 25-knot winds, but anything we've made the commitment to anything over 20 knots we'll go for. Right now, the airplane's looking in good shape. The engine's looking in good shape. We've got the facilities lined up. All of that had to come together in about 2 hours' time, and we've gotten past that. So really, I think our only remaining constraint now is hoping that Mother Nature's going to cooperate. Programs in the past have set 6 months waiting for weather like this to give this kind of testing, and we're on our second day. So it's rather optimistic if we can knock it off on our second day.
As winds in Wichita began to intensify, the team expressed a strong desire to start testing immediately rather than waiting another day.
Like in the next hour, by the time we can get Vance here and get the wind station off, I'd recommend that we tow in position and set up the wind station.
The engine was covered in sensors to measure airflow at various points around the fan. But with winds only reaching 15 to 20 knots, the conditions were not ideal for testing. The team set up a wind gauge to determine the best direction for the plane to face until the engineers decided the wind speed was strong enough. After some deliberation, they decided to proceed, and the engine was started, running at a thrust of 90,000 pounds. That night, the winds calmed, and it seemed they would remain quiet, at least in Kansas. The Boeing team returned home empty-handed for Thanksgiving, having spent nearly $10,000 on the trip. After several more attempts, they eventually found the required crosswinds 2 weeks later in Montana. The test was successfully completed. As the first flight of the 777 rapidly approached, pressure mounted on the team to deliver the redesigned engines. They were working under a management system called Just in Time, where parts were scheduled for delivery only when needed, not before. Rocky Thomas at Boeing began to feel anxious.
Just a second.
Hello, Tom Davenport.
On Davenport, this is Rocky for our 8 o'clock phone call. I guess I'm still struggling with this, with the lateness of some of the blades, vanes, and the turbines and compressors.
The schedules of just in time. And what we're going to have to do is work on a daily basis with those parts that have the possibility of jeopardizing our schedule.
Okay.
But you're right to be concerned about it, because we are as well. And just in time is wonderful as long as it shows up just in time.
Yeah, that's right. Just in time, when it's not in time, it's the shit.
What Rocky needed to know is how we were doing with the testing of the first two engines. And I had to tell him that we weren't doing as well as we had hoped and that Rocky expected. And he then has to mull that over and decide how he wants to play that message to the Boeing organization. And what I really asked for was a little time to see how we do this afternoon, now that I've taken some action. Rocky will run interference. And hopefully this afternoon, when we have a phone call, wrap it all up for the day, I can give him some good news rather than bad news.
Situations like this would really put the working together philosophy to the test.
Even though we have a very good relationship with Pratt and with United and ANA and the rest of the people on the team, that doesn't mean that everything's always rosy and you get along and you just sit in a room and make things happen. There's certainly been I've had a lot of frustration with Pratt and some of the schedules that they haven't met, and that frustration comes out, and it's...
Geez, my wife and I are absolutely totally in love, and we have a superb relationship, and that doesn't stop her from yelling at me every once in a while.
While the engines had consumed much of the attention, the rest of the plane also needed testing in the months leading up to the first flight. On this particular night, the fuselage is being pressurized for the first time. When a plane flies at cruising altitude, the air outside is much lower in pressure than the air inside the cabin. To replicate the pressure difference on the ground, engineers can't lower the pressure around the plane, so they increase the pressure inside, inflating the plane like a balloon. The plane must withstand a pressure difference of more than 12 pounds per square inch, over 2 tons of outward force on a 777 window, and even more on the door.
We start out at 5 pounds PSI is what we go to. It's preliminary check. Then we'll come down, we'll let people out of the airplane at that point, and then we'll go up to 12.1, which is our proof test. 12.1 PSI, that's per square inch, you got to realize. You may see some leaks around doors, things like that. They're audible, very audible if they're leaking. You'll hear them. If you have a head cold, anything like that, do not enter the airplane. Anything like that. On the way up to pressure, clear your ears like this, chew gum, whatever you need. Your ears will pop. If we start going up and your ears do not pop, let us know on the radio. We'll bring it down and let you out. We don't want your ears ringing in there. No earplugs at all. It may be noisy in it, but do not wear earplugs. Okay. When we go to 12.1, I want everybody in the 26 building. I don't want them over here on this beam.
Okay, now we got contractors,
Not that I'm aware of. We want.
Okay, FAA is here. So special coordination.
They understood that they come in, they got to stand by until we're ready.
Okay,
Okay, so we're ready to go, right?
Yes.
Okay. Go ahead, Harold, take her up.
Everything holds up under 5 pounds per square inch. But as the pressure is raised toward the maximum expected pressure difference of 12.1 pounds per square inch.
That's a good sign. No plastic blowing. 131 back there. Equal time to 5 minutes.
At 12 pounds per square inch, a seal on the rear door blows out.
There it goes. See if you can hold it. Go ahead and get to 12. Fire at 1 and hold. Okay, we know we're going to try to get the proof and hold it.
The engineers continue pumping air in, hoping to maintain the target pressure, known as the proof pressure.
I don't know. We're talking about it. Can't hold it. Okay, we're not going to hold proof. We're dropping it. Drop her, Harold. Real close, you know. Real close.
What is the airplane doing? It's climbing up.
We were climbing real good. We were climbing real good.
How high?
We were only going 1,000 feet per minute, but we were at 12.0. That blew.
If this starts moving out here, I mean, it's just going to rotate. Right. And it can rotate at this point. Oh.
Right, and then it just pops
And it's
out.
pushing it out here.
Yeah, at a certain pressure, it'll just pop out.
What I'm saying, either way, it's going to rotate around this point here.
Let's go up and take a look.
Yeah.
Let's go up and take a look and see what we got.
So, I don't think that's going to work. I really don't.
What?
Like you said, it's going to rotate around that point there. What we're going to do is we're going to fill this space so the seal has nowhere to go.
With what?
With Tygon tubing. It'll be trapped by the skin, and it'll have nowhere to go.
Okay. Let's take a break.
The goal now is to create a temporary seal for the door using sticky tape and tubing so that the rest of the plane can be fully pressurized. The makeshift fix worked, and later that night, the plane was repressurized and reached the proof pressure without any leaks. The test result was another gift, to use Alan Mullally's words. The door designers identified the weak point in the complex silicon rubber seal and redesigned it. Every new plane eventually reaches the moment when it's ready to be revealed to the world. This event is called the rollout.
Off to the rollout we go. Get in the back. Get in the back.
So what do you
To get into the game.
Glenda Barnes applies sealing compound around the inside of the 777's fuel tanks. She, her husband, and her father have been invited to the rollout ceremony alongside 100,000 other Boeing employees. Alan Mullally and several Boeing executives will address the crowds 15 times throughout the day. Every hour, another 7,000 people are brought by bus to the factory.
much earlier? I figured we'd go up here.
Hi, how are you? And you are?
I'm Al.
Oh, hi, Alan. It's nice to see you this morning. You have your mic on? He's all mic'd? No. He isn't. Okay, we'll get a mic.
No,
on.
I'm not going to do it yet.
Okay.
Stop in the bathroom.
Welcome. Welcome to the Working Together celebration. We thank you for coming and sharing this day with us. The 777 is the seventh all-new Boeing jetliner.
You actually go on at 4 minutes to the hour.
Right.
And then we'd like, if you can come close to finishing right on the hour, that helps us out a lot.
The ceremony is built around a video, sound, and light show, leading up to the moment when the plane is unveiled.
I guess they're just going to show what, the films, and then what they're going to show here, just the films, and then you go to another area. Ain't no sense of going into the crowd. I don't know what you do.
Among those sharing the spotlight with Mullally is Boeing President Phil Condit.
Good morning, and welcome to the Boeing Working Together celebration. I'm Phil Condon, President of the Boeing Company.
My name is Alan Mullally. I'm the Vice President and General Manager of the 777 Division.
This beautiful airplane comes with a list of new achievements
for Boeing. Now, are you ready? It's going to make your eyes water. We'll follow the directions to the factory. Enjoy yourself.
I got the Boeing fever.
Time to go. Got Boeing fever now.
Boeing fever. Six feet again on real side, right?
Yeah.
Landing. There you go.
Right. Man, floor, it looks more of it. No, you're not going to see it. Okay, yeah, it's funny.
This weekend, taking more than make together celebration. On the language of your coming. And to the man and we worked so hard to bring the 777 to life. A spare right. The Boeing 777 over 3 million parts lying in tight information. And they all work together just like. Come on and take a look at our new airplane and see how we're working together.
From a distance, the 777 may seem deceptively small, but up close it is truly impressive. The 777 is nearly as wide as a 747 and only 20 feet shorter.
I feel we do this like from the SOB, which is side of the body of the plane, which is here, all the way out is what I really call it. Inside of there, see those holes that's underneath there, those little round holes, go in and out of those, seal up down the wing. I mean, that's the excess holes. You get in now. No, you just have a radio with you. The sealers go in and out of there. Seal it. It's hard to get in there and sometimes hard to get out. Because that's what small holes. That's the first thing I looked at when I undid the curtains was the wings. I wanted to see exactly what they look like. To just imagine all the stuff that I'd done inside of there.
I think the expression sort of is, oh wow, it just, and you can't help but get tears in your eyes. Everybody I talked to had the same reaction.
Yeah, get in their eyes. Yeah, it really is.
It's a real draining experience to build an airplane. So I think everyone is ready now. We're ready to go fly it.
So it was thrilling, having worked on the airplane since the start, to see this all culminate here.
It was feeling as it will be at the beginning of June.
When we see the airplane lift off, it'll be a big relief. When we see it land, it'll be a bigger relief.
Late that night, the first 777 exits the hangar for its true rollout, witnessed by just a handful of workers. Over the next 2 months, the plane will be fueled, and all its major systems will undergo one final round of ground testing. If all goes well, it will be ready to fly. The first 777 is now only days away from its first flight. The interior has been filled with banks of test equipment, needed once the test engineers are allowed aboard, though that won't happen for several weeks. During the initial flights, only the pilot and co-pilot will be on board. Nothing is left to chance. Although this plane has been tested inside and out, the 2-person crew will wear parachutes, ready to bail out through a specially designed emergency door if anything goes wrong. But before the plane can take off, it must first be able to taxi. That's what's happening today after the massive cleanup of the taxiway is completed.
We did a little FOD walk, looking for foreign objects that could damage our engine. And obviously that wouldn't be acceptable. So we have a bunch of volunteers, novices, walking down the ramps, everybody, great intentions, and it all helps. Anything could be ingested. Right now, we don't want to take enough chance to damage the blades at all or the compressors.
Okay, we've got left and right engine started. We're reviewing our status messages.
Creek coming up here in a moment.
Today the plane will taxi down the runway, approaching takeoff speed, and then apply the brakes. It's a prelude to tomorrow's event, the first flight. But as the engines begin to turn, a problem arises.
All stations, this is 771. We had a hydraulic leak on the left side of the airplane, and we're shut down or opening doors here to investigate. Stand by here for that, how long we're going to be.
Looks like it's going up and up or line of front. See it?
Yeah.
The source of the leakage is found. A small rubber O-ring had been pinched at the junction point, leaving a gap for hydraulic fluid to escape. The engines are restarted, and the crew goes through their final checks. Under its own power, the first 777 makes a swift right turn and heads toward the runway. These taxi tests are designed to check the landing gear, brake heating, and overall stability of the plane. John Cashman will take the plane up to 140 knots, lifting the nose off the ground. Any faster and it would take off, but that will have to wait until tomorrow.
Okay, great. 1. Great.
However, during the high-speed taxi, a surprise occurs. Some observers suspect that all the wheels are actually off the ground at the fastest point of the taxi, as the first flight happens a day early.
Oh my. Oh my. He's okay, what do you say? Let's repeat in unison. First flight is tomorrow. Yeah, tomorrow. It did not happen. No.
Nice. And I'm going to start just going by...
After one more taxi, the team meets for debriefing.
For the day.
46 after high-speed taxi brakes had have noticeable vibration just prior to stop when using light braking. This was noticed on first taxi also.
And we can call that one an engineering item too, I guess, because we don't necessarily want anybody to do anything on it tonight.
That be some of the oil we got on it.
No, this happens every time you get probably above 3 to 4. It's kind of a grindy, low groan it's just before you stop.
Okay. Thank you, everybody. It was a good test.
Thank you very much. I think we're there. All right. We can't test any more on the ground. That's great.
On the morning of June 12, 1994, the world's press gathers at the Boeing plant. VIPs, including Boeing Chief Executive Frank Schranz, await the announcement of the final takeoff time.
35 feet with 15 knot tailwind. Those are the numbers. So he's going to go try it, okay? Great.
The airplane might
$10 back.
go up this way, then we'll get back on the bus, go out in position on the field for takeoff. Okay, ladies and gentlemen, it is now your cue to go back behind the barricade so the airplane can taxi north down. Please look forward.
During the flight, the Boeing telemetry room maintains constant contact with the plane.
Start engine. Right, the sides of that engine, that suck out cause the fog of water at home. Yeah, it's not so bad. It's not almost no worse than the other engine that are cut. Yeah. But you got to be careful. You're right, though. We've gone to a lot of trouble Boeing-wise to keep them away on all the engines.
Okay, Grant. Nick this back. Give us hand signal. Player, thanks for the help.
Roger. Have a good. Turn it. Not lovely. Yeah, there you go. And it has to. Yeah. I like that. It worked out. Yeah, Michael, walk out. This will need me. Yeah. We'll be pretty bad. Well, is that how they're placing it? Yeah, that's right. Yeah. Wow. Okay, what's coming in? Let's go. You're almost at the limit on the tailwheel. We're starting the engine, but these engines are just performing better than everybody expected. So usually we'd have to turn the airplane around, have the engine blow into it. And getting in said no problem. Started right up. Yeah, had a good start. Still good start. Oh my God! Oh my God! Did it something? Oh my God! Oh gee! Go! Oh my God! Oh, what a what a deal! Oh, there you go! Oh my God! Oh. Wow! Oh, do you think it was pretty? Did you think it was pretty? There's no pretty fix though. The gear out. Yeah, let's get the order book out.
The first 777 test flight lasted nearly 4 hours, with only 3 minor issues identified. Apart from that, the flight was flawless. 2 months later, Alan Mulally was promoted to a more senior role within the company. Many more months of testing lie ahead for this plane and others like it. Finally, passenger flights are scheduled to begin.
The mid-50s, a time of exuberant change. From the Depression of the 30s, the nation had plunged into the strictures and rationing of World War II. Now, for the first time in decades, Americans were enjoying a booming economy, and they ate it up. The jet age had arrived, and Americans were fascinated with the sleek new swept-wing fighters that had cleared the skies in Korea. and broken the sound barrier in level flight. Our great national icon, the automobile, reflected their style. It was the era of poodle skirts, hula hoops, and hydrogen bombs. Behind the fads and conspicuous consumption, perhaps fueling them, lay a dark specter. Our World War II ally, the Soviet Union, was now an implacable enemy, and they had the bomb. The space race was on. The US and Soviet Union were developing missiles to deliver nuclear warheads and to place payloads in orbit. The Soviets were ahead at the first lap. Sputnik, barely the size of a soccer ball, carried only a simple transmitter, but its monotonous beep sent a chilling message. Soviet test sites lay deep in a gigantic and seemingly impenetrable landmass. The US was desperate for intelligence on these threats. A gawky, highly specialized U-2 could overfly the sites at 80,000 feet, but its slow speed and agonizingly long loiter time made it increasingly vulnerable to improving Soviet air defenses. It was only a matter of time. The US government needed a better reconnaissance platform. By 1956, Lockheed was designing such an aircraft, the CL-400. Pratt & Whitney was selected to develop a radical new engine, the liquid hydrogen-powered 304. It demanded an engine with far more thrust than any yet existing. Pratt & Whitney was approached to create a powerful new turbojet, the J-58. Dick Core was chosen as chief engineer for both projects.
Suntan was a project to develop a hydrogen-fueled fan for very high altitude operation, up Mach 2 at 100,000 feet. And the engine was a concept invented by a fellow by the name of Ray, I think that was R-A-E. And he convinced the Air Force that this was the right kind of engine to use at very high altitude. But he had no facilities for developing an engine, and the Air Force turned to Pratt & Whitney to develop this engine, which we call the 304. And at the same time, we had another project. I was assigned another project, which was the J-58 for the Navy. And the Navy at that time was very interested in using what fuels that were doctored with boron.
Development of these new engines began in East Hartford, but it quickly became apparent that the Connecticut facility possessed neither the space, the noise containment, nor the security to see the programs through. A search for a new site led to a tract of land in the northeastern part of Florida's Everglades. The remote location near West Palm Beach was ideal, except for swamps, mosquitoes, alligators, and rattlesnakes. In 1957, a contract was signed for construction of the new facility, and Pratt & Whitney's Florida Research and Development Center was born. Initial development was daunting. There was no direct access to the 7,000-acre site. The state of Florida agreed to build a road, the Beeline Highway, but the segment from West Palm Beach to the plant was delayed when the Loxahatchee Slough refused to cooperate. It swallowed tons of fill and 2 bulldozers. Designer Ray Schneider was one of the first employees hired specifically for the new facility.
Well, the first 6 weeks I was down here, the Beeline Highway wasn't open because of a quicksand problem, and they couldn't build a section of the road. So they routed us through the swamp on a dirt road, and it was very interesting because it was hard to have 2 cars pass at the time. The road was so narrow.
After more tons of fill and months of work, the Beeline was finally completed. Plant construction was nearly as difficult. Unusually rainy weather turned construction sites into a sea of mud. Fill for building sites came from borrow pits, adding numerous new ponds and lakes. Environmental concerns led to creating new wetlands to replace those being filled for construction. Charles Rolke, the first general manager of the new facility, faced a number of obstacles. Pratt & Whitney was unwilling to part with experienced support personnel from Connecticut, and much of the workforce had to be recruited and trained locally. At the same time, the customers wanted work on the 304 and J-58 to progress as quickly as possible. Construction was barely underway when J-58 and 304 engines began arriving from East Hartford. Work on these projects advanced rapidly in makeshift rented shops. First permanent structures completed were the test stands. Air Force built 2 facilities to generate liquid hydrogen for the 304. They were codenamed Mama Bear and Papa Bear, and for security reasons they were given a cover story. Local residents were told they were processing plants for the Apex Fertilizer Company. Despite the primitive conditions, spirits were high. A young engineer, Frank Maccabee, was part of that original cadre.
A group of us, about 30 or 40 engineers and their families, had been transferred down from Hartford. All of us were young. The test engineer group, of course, we had a management team as well, but our families were young. This was an area that had not been developed at all. The communities were practically bare of houses. As a matter of fact, a whole new community was built in Lake Park, where I live, and we were one of the first families to move in there. Everything was new, including the technology, the challenge, the relationship with the customer, the facility itself. It was all very exciting, and we were all eager and didn't know that we couldn't do some of the things that actually were accomplished, and we just had a lot of fun. There was a tremendous camaraderie.
A year before the main office building was complete, both engines were ready for testing. In September 1957, the primitive quiet of the swamp was shattered by the roar of the first 304 test run. Thunder heard for miles under sunny Florida skies. The J-58 too progressed well for the Navy, and the engine made its initial test firing on Christmas Eve, 1957. On May 27, 1958, the Florida Research and Development Center was officially dedicated. The new Florida Facilities Direction may have seemed clearly defined. The nation's was not. Within the next 5 years, we saw the election and endured the assassination of a young new president, watched the communist takeover of Cuba, and sweated through the ensuing missile crisis. We held our breath as tiny Friendship 7 carried 41-year-old John Glenn into history as the first American in orbit. We watched the slow expansion of American involvement in a remote Asian country, and honored the call to place a man on the moon by the end of the decade. Pratt & Whitney faced its own unique challenges. In the early stages of the 304 program, skeptics feared that liquid hydrogen would never be safe. The mere mention of it conjured up visions of the Hindenburg disaster. But Pratt & Whitney devised efficient new ways to handle this volatile fuel, and the 304 proved safe and successful. Both programs were progressing on schedule. Then came a strange musical chairs change. The Navy lost interest in developing their Mach 3 attack plane, and work on the powerful J-58 ground to a halt after just a few test firings. At the same time, things were going badly for the Air Force's CL-400 program. As designed, the aircraft presented support problems, was based on technology already becoming obsolete, and could not carry sufficient fuel for the needed range. The Air Force decided to start with a clean slate and canceled development of the CL-400. Work on the 304 hydrogen engine was suspended. Setback was brief. Pratt & Whitney's new expertise and new facility were just beginning to blossom. The U.S. still required a long-range reconnaissance platform. The Air Force and CIA recruited legendary aircraft designer Kelly Johnson and the super-secret Lockheed Skunk Works to design a new plane, the A-11. To meet the demands of high-altitude Mach 3 flight, they turned to Pratt & Whitney's new J-58 as the most promising engine candidate. At the same time, the need for space launch capabilities was growing rapidly. The Air Force enlisted Pratt & Whitney's newfound expertise with liquid hydrogen to develop a compact, powerful upper-stage booster engine, the LR-115. In 1961, the program was transferred to NASA, and the engine became known as the RL-10. The last contractual 304 tests were still underway when RL-10 development began. The company never missed a beat.
I had the good fortune of being the test engineer responsible for assembling and testing the first RL-10, which we called FX-121. It was a new technology. Hydrogen and oxygen had never been used as a rocket fuel before in any quantity. The cycle that the engine was based on was new, the bootstrap cycle. The materials that we used were used for the first time in this environment. It was just all new and exciting. I remember the first time we fired the RL-10 was on third shift. It was the middle of the night in the swamp. It was black as ink, starry sky, and when that engine lit off, it was like doomsday had arrived. A tremendous sheet of flame out the diffuser, a noise that you just never heard before. At least I hadn't. It would actually get into your lungs and breathe for you. It was just tremendously exciting. And the engine ran and ran and ran and ran. As a matter of fact, I believe it was 426 seconds, which doesn't sound like long, but at that time it was the longest duration firing of any rocket engine anywhere. We had set a new record that night.
While things went well for the new RL-10, adapting the J-58 for the A-11 was not as simple as anticipated. The technical demands of sustained Mach 3 flight were daunting. It required not just new designs, but completely new concepts. A brilliant engineer, Bob Abernathy, devised ducts that allowed inlet air to bypass the compressor in supersonic flight. This simplified the inlet design, and at high Mach numbers, virtually converted the engine from a turbojet to a ramjet.
The engine structure had to stand these very high pressures at 1,500 degrees Fahrenheit temperature. That melts most things. I've found a way to make it possible to weld what we used to use for turbine blades called wasp alloy in sheet structure.
If the J-58 had to operate at temperatures beyond the tolerance of available metals, there was a simple solution: do the impossible. Create new ways to process previously unusable alloys that could do the job. Joe Moore was a young materials engineer when he was faced with these challenges. Considering the complexity of the task, his first exposure to the materials laboratory was disconcerting.
Well, shortly after I came to work, looked at the situation, I thought, my God, we're not a development lab, and that was, I'd been brought there. However, the guy that brought me said he wanted to make it more of a real development laboratory, and I looked at it, and I thought, my gosh, this place is just a control lab. They check pieces that come in and raw stock that comes in to see if they meet the mechanical and chemical requirements, and that's about it. And so I truly did this. It sounds corny, but I made up my mind that I wanted to see us become the best laboratory in the world.
Design of the A-11 at Lockheed faced similar challenges. At Mach 3, portions of the aircraft skin would reach temperatures of nearly 1,000 degrees, well above the melting point of conventional materials. Kelly Johnson's engineers turned to Pratt & Whitney's pioneering work with titanium alloys for the answer. The next few years of RL-10 and J-58 development were fraught with difficulties as FRDC delved into the unknown. Dick Mulready was a driving force behind the new science of cryogenic fuels.
Hydrogen is an excellent working fluid, which means that it doesn't take much of it as a flow material through a turbine to generate a lot of power. And because it was hydrogen, we could take the hydrogen that was going to be burned in the use cool thrust chamber, and the heat that it extracted from the thrust chamber was enough to drive the turbopumps. So the hydrogen flows through the pump, down through the cooling jacket, then up into the chamber. So all of it is used. Nothing is wasted. There's no gas generator that throws away anything. So it's an elegant sight. It really is perfection. And it's the reason the engine has now lasted over 40 years. It's the longest living Mark Pratt Whitney for an engine. We took the engine, which had been run horizontally, put it in pair up in the E5 stand, and made a firing one day. Al Gardner was with me. He was the Air Force project officer, and everything worked fine. Next day, there was a second firing on the E5 stand, and there was an explosion.
That second firing was eagerly attended by a group of NASA officials, led by the renowned German rocket scientist Wernher von Braun. William Missimer was a young instrumentation engineer who witnessed the event.
We pushed the button for the run, and all these dignitaries were there, and the stand blew up. I mean, not a little blow up. This was a big blow up that lit up the sky, and it was 1,000-foot plume went up. And we all turned pale. And I could hear von Braun saying, "Oh, shit." He turned around and walked out. Well, that led to a very long but wonderful episode that had a happy ending, where that place turned to and found out why that problem happened. It was an ignition problem. Believe it or not, all previous tests, the RL-10 was laying horizontal, and it ignited very, very reliably. Put it in a vertical position, you got the wrong mixture ratio for ignition. One lit, and the other one just put down. It will come and exhaust unburned propellants, and it went off like a bomb. Getting to that answer was one of the most exciting technical witch hunts I've ever been through.
The RL-10's ignition problems were ultimately solved, and the engine passed its preliminary flight rating test in January 1962. The J-58 passed its preliminary flight rating test just a few months later. Under a cloak of secrecy, flight testing of the A-11 progressed rapidly, and an experimental interceptor version, the YF-12A, entered operational service. The reconnaissance version became operational in January 1966, the legendary SR-71 Blackbird. Though now retired from the U.S. Air Force, the SR-71 still holds numerous speed and altitude records thanks to the J-58. 2,193 miles per hour in level flight, and sustained level flight at 85,069 feet. In 1990, it flew from Los Angeles to Washington, D.C. in 1 hour, 4 minutes, and 19.89 seconds. The RL-10 was also about to make history, but not without some tense moments first.
The first launch, of course, was disastrous because the Atlas launch vehicle suffered a failure on liftoff and exploded essentially on the pad. Funny story about that. One of our people was in the telemetry shack at the Cape, and his job was to monitor the telemetry from the engine during the launch and report back to Bill Gorton, who was the vice president and general manager down here then, what kind of performance we were seeing from the engine once it fired in space. So the Atlas fired and lifted off about 3 feet off the pad, and the sustainer engine shut down, and the vehicle slowly settled back down into the launch pad into a tremendous explosion. You can imagine how big a fireball that much hydrogen and oxygen makes. Well, the telemetry package on the Centaur vehicle, the upper stage, which our engines were on, was battery powered, and it was external to the vehicle. And when the explosion occurred, it was blown free of the vehicle into a field about 300 yards away, and it lay there radiating. It was still sending out signals. Our fellow in the telemetry shack was watching those signals on a trace, on an oscilloscope, and it didn't show anything other than that everything was normal. The engine, of course, hadn't fired at that time and wasn't supposed to, so all the traces were flat and looked normal. So he was reporting back to Bill Gorton and the rest of the management group down here that everything was fine. In the meantime, the vehicle was a smoking pile of rubbish on a launch pad.
Finally, in November 1963, two RL-10s successfully boosted a Centaur upper stage into orbit.
Again, a group of us had gone there somewhat apprehensive because we had had so many problems in the past, and this launch was picture perfect. Everything went according to schedule. And when the telemetry traces showed that the RL-10s had fired right on schedule, the chamber pressure came up and held constant, right where it was supposed to, it was the greatest feeling you can imagine.
2 months later, the 6 RL-10s of a Saturn S4 stage propelled a 37,000-pound payload into orbit, successfully demonstrating the practicality of hydrogen-oxygen fuel for the Apollo Moon exploration program. The RL-10 went on to set the standard for performance and reliability in upper-stage propulsion systems. It boosted 7 surveyor missions to the lunar surface in preparation for Apollo, powered Mariner and Pioneer to our neighboring planets, and sent Voyager to the farthest reaches of our solar system and beyond. The success of the RL-10 and J-58 quickly led to other pioneering programs. FRDC began development of a high-pressure rocket engine quite different from the RL-10. Instead of an expander cycle, the engine used a pre-burner to drive turbopumps delivering the cryogenic fuels. It had tremendous growth potential. From a 50,000-pound thrust demonstrator, the concept grew to 250,000 pounds in just a few years. In June of 1964, the FAA awarded both Pratt & Whitney and General Electric contracts to develop an engine for a proposed supersonic transport. With the experience of the J-58, Pratt & Whitney's designers appeared to have a substantial edge in development of this 54,000-pound thrust high-Mach power plant, and they tackled the project with enthusiasm. Deployment rose to 7,000. The engine was completed ahead of schedule and ran on March 31, 1966. By December, the test phase was complete, and the engine had run at speeds up to Mach 2.7 at 65,000 feet. The Christmas holidays began on a jubilant note. On New Year's Eve, that euphoria was shattered with the announcement that GE had won the SST engine contract.
The unfortunate thing is that even though the SST program didn't proceed, GE got millions of dollars in development for high-temperature jets that we didn't get.
Other development programs, such as the C-Jet marine engine, were lacking in a viable market. In an effort to keep the facility alive, responsibility for all J-58 overhaul was transferred from East Hartford to FRDC, with production and assembly of several other military engine components. In September 1967, FRDC received a contract for development of the ST-9, a new turboshaft engine for the proposed U.S. Army UTOPS helicopter. The company also started contract work on a 250,000-pound thrust rocket engine and began research on the use of gas dynamic lasers as weapon systems. But none of these programs offered the immediate business benefits the company required. The future of FRDC was still in jeopardy. 1967 was a rough year for the Air Force, too. Soviets introduced the MiG-25, a formidable new fighter which shattered numerous performance records and threatened NATO air dominance. In the skies over North Vietnam, it was increasingly evident that the dogfighting capability of current U.S. fighters was marginal at best. The Air Force quickly initiated a competition for a new air superiority fighter, the FX competition. The Navy, too, was seeking a new engine for its proposed F-14. Once again, Pratt & Whitney was pitted against GE. This was a must-win situation, and FRDC responded admirably. Their entry? The remarkable F-100. 1968, FRDC's 10th anniversary. 10 long years. one short decade. America was now deeply enmeshed in Vietnam, but results seemed frustratingly elusive. World War II had ended with a dearly bought but unequivocal victory. Korea concluded with an unsatisfactory and unsettling stalemate. With Vietnam, the public became increasingly skeptical of official reassurances. Government news releases reported a light at the end of the tunnel, but the massive communist Tet Offensive of 1968 finally shattered public complacency and polarized the nation. Ahead, the nation faced a painful extrication from Southeast Asia. There were moments of glory, though. In 1969, we watched our TVs in awe and anticipation as Neil Armstrong took that first small step, forever changed mankind's place in the universe. Our old icon, the automobile, no longer sported fins, but cars were still aerodynamic and powerful. If the events of the late 60s and early 70s left the public disillusioned with the military-industrial complex, Captain Whitney knew the future was not that simple. Regardless of public opinion, the nation still faced very real threats and possibilities. The F-100 competition was challenging. The Air Force demanded an engine with a higher thrust-to-weight ratio than any previously designed. Winning the contract was critical to FRDC's survival.
The biggest problem in the F-100 is to get the weight down. The original design we had didn't make it. We had some pretty good information that told us we were off the mark on the weight. And Bill Brown, I will call credit for getting a design change that got the weight down. But doing this getting the weight down is what made it risky. The other parameters were well within hand. Trying to do this job with the weight that we went after was a real tough program. And to do this, we did need to have IN-100 in the turbine discs.
Another materials laboratory breakthrough, gatorizing, provided one key to solving the weight problem.
We did a very unusual thing, and frankly, I don't remember why we did it, but we did. We took the material and we did not heat treat it, and we tested it. And we tested tensile properties up in the 1700 to 2200 degree range, and stress rupture and tensile. And we were absolutely amazed when the rupture results came in, because as soon as the guy loaded the specimen, it just stretched like chewing gum. And we became very excited over this, because these alloys, like IN-100, are very difficult to move, to forge without cracking and so on. It was this stuff just, stretching like putty. So it occurred to us, gee, if you can get the material in that kind of condition, if you can pull it like that in tensile, why can't you put it into compression, which is a forge motion, and do the same thing and come out with forgings that are very, very close to net shape, with a reduction of machining and something that had no cracks in it. Like I said, I have a super strong alloy, like IN-100. So we set up a little forging rig, put the material in a superplastic condition, heated up the whole system, and held it at temperature. We were able to make little small pancakes with different beautiful surfaces and type configurations. So that said to us, boy, we got something here. And we went after a big forge cycle, and then, of course, we sold it to the Air Force for F-100 disc. And in fact, we sold it to them, and we won the contract before we ever made a full-scale disc. We released everything on small-scale pieces, which is kind of dangerous.
Dangerous it may have been, but the full-scale IN-100 discs proved every bit as good as the tests promised. The result was a lightweight engine with an 8-to-1 thrust-to-weight ratio, producing nearly 25,000 pounds of thrust. It was a 25% improvement over any previous engine. The first F-100 engine ran June 30th, 1969, and began a grueling test series. Problems encountered were quickly fixed. The schedule was maintained. In March of 1970, the Air Force announced Pratt & Whitney's selection to power the new F-15 Eagle. Simultaneously, the U.S. Navy selected a version of the same engine, the F-401, for the new F-14 Tomcat. Full-scale development began immediately. It was a rigorous schedule, running in parallel with airframe development. In November 1974, the first production F-15s were delivered on time to the U.S. Air Force. The Navy version of the engine, however, experienced delays. The Navy canceled its order for the F-401 and opted for East Hartford's existing TF-30. In May 1970, NASA requested design proposals from Pratt & Whitney, Rocketdyne, and Aerojet. High-pressure, reusable, hydrogen-oxygen-powered main engine for the future space shuttle.
Dick Mulready, along with some folks from the research lab, had started a program of high-pressure, high-chamber pressure rocketry, and demonstrated very successfully that a very high-pressure engine could be built and cooled and would be very efficient. So when the Space Shuttle main engine program came along and the request for quotation went out for the engine, responded with a proposal based on that technology. The company had put about 10 years of effort into it and a lot of company money. It was R&D, of course, but it was still all paid for by the company, and we had actually demonstrated the concept at full price. So we submitted our proposal to NASA, and in this new environment that we were learning to live in, where contractor is just a person that NASA uses when it's convenient for them, they gave our design, our proposal, of course, which we had written under their aegis and they had paid for, they gave that information to our competition. And they said, we like this design concept, this high-pressure engine concept, better than the concepts which you have put forward. So we want you, the competitors to Pratt & Whitney, to take their concept and make a proposal based on that. Well, that was an insult beyond insult as far as we were concerned. But it happened, and we had to live with it.
Despite this turn of events, Pratt & Whitney was confident that their experience and established technical expertise would prevail. It came as a tremendous shock when the contract was awarded to Rocketdyne in July 1971. A satisfactory explanation for the choice was never offered. Pratt & Whitney appealed the decision to the U.S. Comptroller General. After a 6-month legal battle, Pratt & Whitney lost the appeal. The decision effectively took FRDC out of the space business for years to come, except for continuing development of the workhorse RL-10. That loss, however, may have had some positive aspects.
My view is it's a doggone good thing we didn't get that competition because we were right in the middle of the F-100 program at that time. And there was absolutely no way in the world that we could have handled the two of them. They both would have failed, and we would have gone down the tubes.
In December of the same year, the U.S. Army selected GE's entry over Pratt & Whitney's ST-9 to power its new utility helicopter. Plus side, however, in addition to the huge new F-100 contract, FRDC's laser research was generating interest. In December 1972, the Air Force funded a program to place a gas dynamic laser aboard a flying test bed, the Airborne Laser Laboratory. One key architect of Pratt & Whitney's laser program was William Missimer.
Actually, after we lost the engine contract for the Space Shuttle main engine to Rocketdyne, it was a big blow to the company, but we had developed facilities and capabilities in the area that fit the type of laser that was in vogue at that time very well. It was a gas dynamic laser, which, believe it or not, from a propulsion standpoint, almost like a rocket engine. It's had some cryogenic fluids and had very tight tolerances. And the only thing that was new to us and foreign was the optics part. One of my first jobs was setting up the optics for some of these tests. And I remember we had the Army in one day, and they set up their experiment downrange. I think it was a tank or a piece of a tank or something. And we had set up the telescope, and there was a wind blowing quite a bit. We all went up to the control room, closed up, buttoned up the facility the same way you would for a rocket test. It's all remote controlled. And the Army guys were sitting there, and we pressed the button, and the laser came on, and the beam didn't appear for a while downrange. And then all of a sudden it was there, and it did its thing. Couldn't figure out what the delay was. So I went down, and here the wind had blown the door shut the steel door shut on the telescope room. The Hummer burned a hole through the door and then went downrange and did its job. Well, after we did the initial research work on what was then called the XLD-1, that was a 1 megawatt boilerplate laser that we put into E8 stand, and proved the capability of the high energy lasers. The Air Force got very interested in a lightweight version of that would go into a modified 707 airplane. But then the challenge became, how do you lightweight this thing so it's flyable and also make it safe? Now, here's where the jet engine smarts came in, because they looked at Pratt as being able to man-rate something from a safety standpoint, which was extremely important. They could not, or we could not, afford any kind of an accident in flight for this demonstrator. It was a highly classified program. So we won the contract, and in those days, it was a pretty sizable contract to make this a flyable, lightweight system.
In 1973, General Dynamics chose the F-100 engine for the YF-16, its entry in the Air Combat Fighter competition. The YF-16 won the competition in early 1975. Pratt & Whitney's F-100 was a key part of its success. That same year, the F-100 further proved its quality when the F-15 Streak Eagle set 8 time-to-climb records. In its final flight, the Streak Eagle accelerated from a dead standstill on the runway, 98,424 feet, 19 miles straight up in less than 3.5 minutes. It smashed the MiG-25's old record by nearly 30 seconds. 4 NATO countries, Norway, Denmark, the Netherlands, and Belgium, had recently formed a consortium to seek a new fighter. The performance and cost of the new F-16 and its F-100 engine caught their eye. As an incentive, Pratt & Whitney and General Dynamics offered an unprecedented international co-production agreement. The F-16 was quickly flying with, being co-produced by, our allies. Now, with East Hartford's TF-30 and FRDC's F-100, Pratt & Whitney held the enviable position of powering the 3 best fighters in the free world: F-14 Tomcat, the F-15 Eagle, and the F-16 Fighting Falcon. To meet the demands of the F-100 program, FRDC had grown further, and in 1976, as part of a major reorganization, it was renamed Pratt & Whitney Government Products Division. The new division was given management responsibility for all military engine programs, including the J-52, J-57, J-75, TF-30, and others. By 1978, 20th anniversary, things had changed dramatically for the company, the nation. The fuel crisis of the 70s affected our economy and our psyche. Cars reflected that change. The great land yachts and gas-guzzling muscle cars of the 60s were giving way to smaller, more fuel-efficient cars, many more of them with foreign names. 4 years earlier, after more than a decade of fighting, the Vietnam War had reached a dismal end. Public sentiment was now strongly against military spending and military involvement. Interest rates were rising. The country was slipping into recession. It profoundly affected the way consumers made their purchases. Pratt & Whitney's biggest consumer, the U.S. government, was no exception. Pratt & Whitney had been riding high on the new F-100 contracts, had slowly lost touch with the customer's needs, and was in for a shock. Frank McAbee had just become president of GPD,
Traditionally, when you won a military engine contract, you had that business and your business base that you could forecast, and you knew you were going to have the production volume in future years to support you. That particular tradition was about to change, though, and was changing very rapidly in the early 80s. When I became president of GPD, it had almost reached the boiling point. Those of us who worked in Washington were well aware of the fact that the F-100, which had just been introduced into service, while it was performing beautifully, was having some problems. We knew that the military was not particularly happy to have those problems, which the opponents to the military program in the Congress could use as an example of how the military really didn't know how to run a program and that everything they did turned out bad. So the pressure was on both sides. We knew that the military was seriously considering giving some of our business to GE. We knew that GE had developed their F-110 engine in competition with the F-100 earlier on, and that they had continued to develop it to some degree with their own company money to have in case our engine didn't work out. And they pursued a very active and vigorous lobbying campaign with both the Congress and the military to displace us, to show that our problems were bigger than we were able to handle. Any issues that arose where there was any type of question as to Pratt & Whitney's responsiveness to the government's problems or to the military's problems, competition obviously took advantage of that and played that up. So it was a very tense time. And the engine was working fine. It was actually working too well because it had such a high thrust-to-weight ratio, so much better than any previous engine, that the pilots and the operating units were flying the airplane well outside the envelope. They never wanted to pull the throttle back. They wanted to use the afterburner a lot. And you know how pilots are. They're like the rest of us. They like sports cars, and they want to zoom around the sky. But as a result of that, the engine was being pushed beyond some of its design limits, and it was having some premature failure. So we had that to contend with. The Air Force, in the meantime, had decided that the way to get our attention, to threaten to give part of the business to GE. Our management did not respond well to that. We just didn't understand, and I'm sure that it wasn't unusual that anyone would have understood that particular circumstance. You know, we had won the competition. It was our engine. We would fix the problem. So why not just leave us where we were? Leave us alone. Let us do the job. Just give us money and go away, which is not all that different than the Pratt attitude over the years. In any event, the Air Force decided they were going to run a competition, and thus began the Great Engine War, as it's known. It was Pratt against GE. And the proposal that we submitted was based on, to a great degree, us getting all the business. And that really wasn't what the customer wanted. And as a result, GE was given 65% of the contract of the first year. That was a great disappointment. It was a tremendous shock to us, to everybody in the plan. Everybody. A lot of gloom and doom.
The Great Engine War, as it came to be known, had a profound influence on every aspect of GPD's existence. Winning back the customer's confidence was not an easy task. Required a drastic change in corporate culture. Quality, customer support, and cost were critically examined and constantly emphasized at every level of business. The company even tried to change their image with a modernized version of the logo. Employees were less than happy. To counter the antipathy that had evolved, Pratt & Whitney began sending engineers and designers to air bases to see their products in real-life operation. Air Force and Navy aircraft were brought to the Florida facility so employees could see the end results of their labors and meet the men who flew them.
I remember the first time we had an F-14 come into GPD. The pilot of that airplane was named Hank Kleeman, Commander Hank Kleeman. He had been the pilot who shot down a Syrian jet about 6 months or a year prior to the time that he visited the plant here. He was a hero. He came here with his radar officer, the other member of the crew. They landed at Gwin, and we towed the airplane up in front of the plant, and then the two pilots went around and talked to people. And I'll never forget, there was a lady who worked in plant engineering. Not a very high position, but nonetheless a good employee. And she broke into tears while she was talking to Hank Kleeman. He was so proud of the part that she had played, that Pratt & Whitney had played, and that victory that Kleeman was part of, that she actually broke down and cried. And to me, that was a tremendous insight into the value of having people feel part of what you're doing.
Eventually, the company proved their new demeanor was real, and the traditional logo was restored. This process of soul-searching, of analysis of attitudes, reached beyond the customer. At this point, Bill Missimer was executive vice president.
When Harry Gray came to UTC, before that was actually United Aircraft, he brought with him the many new ideas, one of which was to make profit centers, and that's when we became Government Products Division. And another one was he had a code. He said that we have a responsibility to customers, shareholders, employees, and the community. Bill Dwyer was an exceptionally fine individual who fit his role as Vice President for Community Relations extremely well. And he was a very humorous guy. He always had an appropriate joke. He was an outstanding speaker, and you could tell that he loved people. He got us involved with, obviously, United Way. He was involved with the Urban League, Special Olympics. Some of his legacies today, the science fair, for example, that the engineers do such a good job of encouraging, are all legacies of Bill Dwyer. They're very well thought of in the community, and as you know, there's now a senior high school named in his honor, not too far from here.
Through the late 70s and the 80s, improvements continued on the F-100, and it grew into a family of engines. The PW200 model featured performance and durability improvements. In part, these improvements came from new materials laboratory innovations, like RSR and Gator Guard, an improved plasma spray coating system that found many uses. RSR was an innovative method for processing inert powdered metal alloys. Bill Moore explains.
RSR stands for Rapid Solidification Rate, and you make powder under inert conditions. We invented a machine, our boys did, came up with a fantastic machine for making powder and rapidly solidifying. And what happened was it consisted of a spinning disc. The metal would be poured in a vacuum chamber from the crucible into a nozzle, onto a spinning disc. And the rotation of the disc, centrifugal force, throws the metal out in 360 degrees all around. We had a blast of argon, or circular curtain, around the spinning disc in order to increase the speed of solidification. And what we were doing was, as we had always done since the J-58 development, was we were reaching for a stronger turbine bleed material using the RSR.
East Hartford's materials laboratory created another breakthrough technique, single crystal turbine blades. This innovation was quickly adapted for use in military engines, dramatically increased the hot section life of the F-100. The development of single crystal blades, coupled with a new digital electronic engine control, the DEEC, ushered in the F-100 PW220. The PW220 set a new standard for durability, reliability, and safety. Work also continued on a higher thrust version of the F-100. With almost 5,000 pounds more thrust, PW229 entered operational service in the F-15E and the F-16C by the end of the decade. A 20,000-pound thrust straight turbojet version of the F-100, the PW1120, was not so lucky. It was selected to power Israel's Lavi fighter, but that program died in the Israeli Knesset. Two other programs of the 80s did not fare well either. APD developed the PW3005 for the B-22 Osprey, the T-800 for the Army's LHX helicopter. These turboshaft engines lost their competitions. During this decade, the Navy began re-engining F-14s with GE's F-110. Production finally ended for the venerable J-52 used in the A-6 Intruder, EA-6B Prowler. For the first time since Pratt & Whitney's founding, the company was no longer building engines for the U.S. Navy. NASA was now seeking improved turbopumps for the Space Shuttle main engine. Engine start. Current Rocketdyne pumps had to be rebuilt after each flight. John Balaguer was the division executive vice president at the time.
Mission and liftoff.
There became an opportunity, which was called the alternate turbopump program for the Rocketdyne engine with power separation. And we went after that tooth and nail. That was the program that we felt we had to win in order to start our space program growth that we so desperately needed. And we worked very hard on that. We brought in a lot of people who were very knowledgeable in the industry, people who had retired, people who were out of NASA and retired, to put together one of the best proposals I think I've seen. One.
Pratt & Whitney resumed work on their SSME pumps and was now able to offer NASA turbopumps that could fly 55 missions between overhauls. But much development work still lay ahead. The RL-10 was continually evolving too, and an unparalleled success record. Over 500 successful firings in space.
We have 2 Centaur engines up and running.
Space provided another outlet for the company's technical excellence and creativity. NASA tapped Pratt & Whitney to develop an engine for the proposed National Aerospace plane. NASP stretched the boundaries of conventional engine design. The aircraft was designed to take off and land like a conventional airliner at existing airports, but would fly to the very edge of space at speeds of Mach 25. It called for an engine of unprecedented versatility, one that would start as a conventional turbojet, convert to a ramjet, ultimately to a true rocket engine. Pratt & Whitney had one of the country's few Cray supercomputers. Design work that would have taken years was condensed into months. New materials and concepts were explored. Subscale testing was already underway when congressional budget cuts put the program on hold. The nature of air warfare was evolving in the early 80s, and agility was becoming an increasingly important issue. Research began on vectoring nozzles for jet engines. Roger Bursey was in charge of this program.
Well, there was a lot of discussions back in the 60s by a German aerodynamicist, Dr. Wolfgang Herbst. He felt that the new aircraft of the future had to have a lot of agility. In the upper left-hand corner where it's the minimum of aerodynamic power, he felt that some maneuvers would enhance the agility of aircraft in that what was known as the post-stall region of the flight envelope. And he felt that one of the means of achieving this agility was to have the use of the thrusts of the engines to augment the aerodynamic surfaces. In order to accomplish that, it could have been done with a series of external paddles, could deflect the thrust. However, that was cumbersome, added weight, added drag. Hence, the aerodynamicists of that era determined that if we could come up with a system to vector the thrust of the engine and have it transparent to the pilot, we could accomplish those feats. With that in mind, our advanced technology team here started a series of testing with scale models and then eventually led to a very successful flight test. And I can recall the first flight. It was absolutely rewarding. May 10th, 1989, out at Edwards Air Force Base to see the two-dimensional nozzle fly. The folks indicated that if now we had the success of taking thrust vectoring into the pitch mode, and they says, if we can do this, why can't we do this? And that's called the yaw mode. Coupled with the pitch and the yaw, we says, if you can do both, why can't you have a multi-axis thrust vectoring? So we launched a review in 1992 with a ground demonstrator made up of various components and successfully demonstrated the multi-axis thrust vectoring.
The Air Force's changing mission meant quicker response time on a global scale. The current generation of airlifters was not versatile enough to meet the new demands. Design work began on the C-17, an aircraft capable of moving huge loads anywhere in the world and landing on short, unimproved strips practically at the front lines. Pratt & Whitney developed a militarized version of the proven PW-2037, the F-117. It provided the power, durability, and reversing capability needed by the Globemaster III. By the end of the 80s, the F-100 and the F-15 would have seen 15 years of service. By the new millennium, be over a quarter-century old, by fighter aircraft standards. Quietly in the background, work was underway on a superb new fighter engine, next generation beyond the F-100. Guiding this effort was Frank Gillette.
We built this engine on the information that we got out of the ATAG program, which is Advanced Technology Engine Gas Generator. At our plant, we call it 689. The compressor, the combustor, and turbine were designed before 83 that we just picked up and just refined so that we had a real good common core, which gave us a basis to do everything. Our design objectives at that time was a balanced design. We wanted cost, we wanted durability, and of the most important we wanted to do this time that hadn't been done is increase our supportability. Of the performance, we wanted the highest specific thrust engine that has ever been made. We ran our first demo engine in October of 1986, and it was a thrill to see this very powerful engine run down in the test stand with a 2D CD nozzle. It was very exciting for us, and we were very proud of all the work and accomplishments of our people.
The PW-5000 was well underway when the government announced a competition for an advanced tactical fighter to replace the aging F-15 in the next century. Two aircraft company teams, led by Northrop and Lockheed, would compete along with two engine manufacturers. Each engine would fly in both aircraft. It was Pratt & Whitney versus General Electric again. The PW-5000 officially became the YF-119, and design and testing shifted into high gear.
The airplane wanted supersonic persistence. It means an airplane can go faster than Mach 1 without using the afterburner, and that was the exciting thing. That's the big change in technology the ATF would have over any other airplane. In other words, the ATF, or now the F-22, can fly the same place that an F-15 can go without using the afterburner. The other big change to this airplane is low observables, which means a stealthy airplane. And we've accomplished that over a lot of technology and a lot of luck. This will be an awesome airplane. This airplane will be as good as an F-117 stealth fighter, but it'll go supersonic and it'll turn and burn. It'll put an air dominance to this United States that we will always have superiority. We won't talk about superiority, we'll talk about air dominance.
1988, 30th year in Florida. The facility was now called Pratt & Whitney Government Engine Business. With the advent of détente, the old Soviet peril that had driven so many of our enterprises was rapidly diminishing, would soon vanish.
The space industry had a saying, and it was that we've lost an enemy. It required that we do some major restructuring of the company. And we did. Unfortunately, we were not unique. We ended up in our restructuring program, which at that time was not called a restructuring program, but today it's a household word. We lost about a third of our business, and we lost about a third of our resources. Most of that was people. I think we handled those restructuring actions in probably the best humane way we could. Spent a lot of time making sure that the hurt to people was minimized, and it still hurt. So we knew we had done the best job we could to minimize that and to try to keep families whole. And so it was a tough time for Pratt & Whitney, especially tough for the military side of the business. And the Air Force picture, the U.S. Air Force picture, was not pretty, which was our #1 customer. So we really focused on international sales, which were really probably the savior and a large part of the F-100 program. We did very well in the international campaigns. Not that we won them without some difficulty and some financial contribution, but we did do very, very well as a team, able to bring in additional volume to put in on top of the U.S. Air Force volume. At the same time, we wanted to be sure that we didn't lose sight of the ultimate goal, which we've been working on for many years, under the leadership of people like Frank Gillette and Gary Plord, working the next engine, the next advanced engine, or what that program was called at that time was the Advanced Tactical Fighter.
Contrary to public euphoria, the end of the Cold War revealed a world more unstable and full of unconfined threats. A nation was reawakening to its resolve as a world leader. Pratt & Whitney's Florida facility had responded to the challenges of the previous decade. The spirit of teamwork that exemplified the early days of FRDC was reborn. New prizes were there for the company to win, if they proved worthy. In 1990, as Pratt & Whitney accelerated their pursuit of space business, United Technologies formed Space Propulsion and Systems, uniting its Chemical Systems Division and United Space Boosters Industries with Pratt & Whitney's space business. Doug North became its president. As the decade closed, ATF flight competition was underway, and problems that emerged were corrected, often with the help of the advanced computing power now available. So, by the instincts of good people.
My closest moment, I'll have to say, during the 15 years of being engineering manager of the 119, was an engine called YF4. It was the first engine that went into supposed to go into the YF-22. We had run the engine down here to pass our qualifications to ship it to Edward. Then the engine passed the qualification. This was on a Thursday, and the C-141 was supposed to come in on Tuesday of the next week. So we had a lot of work to do to get ready, packed to go out. And obviously, GE was already flying in the YF-22, and we had to fly to be a winner. This guy came up and still kept telling me the engine wasn't right. On Friday, we decided to take the engine apart, and I know a lot of people didn't agree with that, but these two guys really instilled in me we should do it. We took the engine apart. We found out that on the #2 bearing support, we had left all the bolts out, and the only thing that was holding this engine was the snaps. So we saw that on Saturday morning. Thank goodness, with the persistence of these people, we put those bolts in, passed the test, picked that engine up on Saturday night, had it ready Monday. The plane came in on Tuesday. We flew it out to Edwards, and that engine was the first one to go fly with engine #5 in YF-22. So the lesson I learned is listen to your people. Without that, this engine on the first roll-up probably would have come out the inlet. We could have lost the contract. We could have not been here in Florida enjoying this great reputation we have. So what I learned out of that is listen to the workers. When they've got a gut feeling and data that says to change it, please listen and change it. Probably the most exciting times in my life is to go out and see the YF fly for the first time. Very emotional. Brings tears to your eyes. I have trouble talking about it right now. And then we flew the YF-22, and that was really thrilling.
Finally, on April 6, 1991, came the announcement we had waited for. Lockheed's F-22 would be the new air dominance fighter for the 21st century, and Pratt & Whitney's F-119 would give it the needed muscle.
We won the honor to power the OCS.
BBM vectoring nozzles were undergoing flight evaluation on the F-15 Active and would soon be installed on the F-16 Vista, setting the stage for a new generation of thrust vectoring engines and aircraft. The SSME turbopumps also progressed through critical testing here and at NASA facilities. Finally, on July 13, 1996, a single Pratt & Whitney alternate SSME oxidizer turbopump flew aboard the Space Shuttle.
And liftoff of Space Shuttle Discovery to complete NASA's constellation of tracking stations in the sky.
By year's end, another shuttle flight carried Pratt & Whitney pumps on all three main engines. Work was also well underway to certify the fuel turbopumps. The space business was growing. There was potential to help make up for decreased military spending, but it required a radical business approach.
We felt that we were lacking in having no resources dedicated to large liquid boosters, which were, from everything we could see, the booster of the future. There was no money to develop one in the United States. NASA didn't have the money. We certainly couldn't fund a program to develop a new booster engine. It was just too expensive. We examined the Russian stable of technology and engines they had, and we found that there was an excellent engine put out by Energomash, a company just outside of Moscow. And that engine led to developing a two-barrel version of that four-barrel RD-170, which was called the RD-180.
Pratt & Whitney entered into a joint venture with Russia's NPO Energomash to adapt and market Russian RD-120 and RD-180 rocket engines. It was a high-risk gamble, considering the unsettled nature of Russia's new politics. But NPO Energomash is the acknowledged world leader in heavy-lift liquid-fuel rocket engines. The RD-120 arrived at the Florida facility, was mounted in the E-8 test stand. October 11, 1995, became the first Russian rocket engine ever fired in the U.S.
Start. 1, 2, 3.
A much larger RD-180 produces nearly 1 million pounds of thrust and has already been selected for the Atlas 2AR and 3A launch vehicles. The RD-180 has also been selected to power the new EELV, the Evolved Expendable Launch Vehicle. Now, with nearly 600 successful firings. Since its inception, Pratt & Whitney's space propulsion efforts existed to serve government customers and operated in conjunction with the jet engine side of the business. Now, with a renewed commitment to space propulsion, a broader base of products, and a rapidly growing commercial market, the company created a new business unit, Pratt & Whitney Liquid Space Propulsion. Angie Negron is the Vice President and General Manager of LSP.
We have been very active in hypersonics. We have 2 active programs, demonstrator programs, one of them for the Air Force Research Lab, and a derivative of that program is called the ARMED program. Both of those use kerosene fuel and are storable. And again, they really are opportunities that we see to grow this business. The RL-10 has been around for 40 years. The idea of replacing the RL-10 is somewhat sad, but also, I think, sends a real message that Pratt & Whitney is serious about the space business. I've gotten tentative approval, and it has to go to the board, to build an engine that we call CCAWS, Commercial Cryogenic Advanced Upper Stage Engine. I think we have the most determined people that I have ever worked with. And as a result of that, they are continuously beating at my door to talk to me about new things and new ways that we can grow this business. You know, they've seen the potential, they've had the vision, and they've just been waiting for the company to catch up.
Even after nearly a quarter century, venerable F-100 was still evolving. AW229A adapts F-119 fan technology for a thrust increase up to 34,000 pounds, 10,000 pounds more than the original F-100 of 1974. It offers improved maintainability and is a strong contender in Pratt & Whitney's growing overseas marketing effort. And while all of this was going on, derivatives of the formidable F-119 were selected to power both contenders in the new Joint Strike Fighter competition, the U.S. Air Force, the U.S. Navy, the U.S. Marine Corps, and the British Royal Navy. For more than 20 years, Pratt & Whitney would be producing a new engine for the Navy. The first production F-22 was unveiled at Lockheed Martin's Marietta, Georgia plant on April 9, 1997.
Today, we are pleased to officially name the F-22 after a special class of fierce and proud winged warriors. Today, we name the F-22 the Raptor.
What you are building, if you build it right, if you dedicate yourself to perfection, will allow people across the planet to be free for the next half century. Allow America to lead the world for the next half century. And someday down the road, because of your dedication and your hard work, the pilot is going to return safe, who might otherwise have died. What you are doing is patriotism at its most important and at its best. And on behalf of that pilot and their spouse and their children, I want to thank each and every worker everywhere across this country who are helping America remain the leader of freedom.
On September 7, 1997, we witnessed the flawless first flight of Raptor 01.
Okay, control, I'm ready for engine start. You're clear left engine start. Here comes the throttle leg. Right. Throttle is in idle. Rotation. 10%. Flight off at 22. Okay, canopy's coming down. Dobbins ground, Raptor 22, flight of 3, F-22 from spot 53 on the south side. Raptor 06 and 19, the F-16s from the guard ramp. Taxi. Am I cleared to go? You are clear. Power's coming up. Release brakes now. Everything looks good. A little fast on the climb. Coming back. Baby gets right on up here. Feels real good, PA. Good ride. Yep, great ride. Tower Raptor 22 is rolling out at 3.6 miles.
Raptor 22, you clear to land, wind 14084.
And now, 1998. 40 years, 4 decades, a full generation and more of engineers, designers, assemblers. It was a year marked by yet another landmark event. The first two JSF-119 engines to test in an unprecedented time, a mere 18 months after the contract award. This was also the first time in history that two different new Pratt & Whitney engines went to test at the same time. Together, the F-119, Lockheed JSF-119, and the Boeing JSF-119 represent the evolution of a new dynasty, a new family of engines in the tradition of the Wasp and the F-100. 1998. The Florida facility is now called Pratt & Whitney Large Military Engines. Division President Ansel Tukes shares his vision of the future.
Being assigned to Pratt, Florida was certainly a joy to me. When I came to Florida, I found a wonderful place, a place that my predecessors and all the people that have worked here for many years had built a very fine business. So first of all, I came into a very nice situation. We have a wonderful market position in our military business here, built on a long tradition of strong technology. I can't think of a better place to be in the aerospace industry than at Pratt & Whitney, and particularly on the government side of the business. So we're in the front line of the fighters for the U.S. Air Force. We have a majority of wins around the world for application of the F-100 engine in both F-15s and F-16s. We have the 119 engine, which is a foundation of power for the F-22 and for the Joint Strike Fighter. Our tradition here, based on gas turbine technology, is just as important on the space side. As you well know, our liquid space operations are centered here, and Angie Negron is doing a fantastic job leading that business and developing markets and technology. I think one of the most important parts of our success, the way we relate to one another. And Pratt & Whitney here in West Palm Beach, our Florida operations are truly a family. That's why it's easy for us to build strong development teams. Our IPD process is based on communicating between people, and we certainly have a spirit of core that I believe is key to our success in the past, today, and for the future.
40 years.
I kind of divided into 4 chapters, if you will, from a culture. The 60s were highly exciting, experimental work, more challenges than you could possibly imagine. Technically, how to get things done, we were pushing the frontiers in everything. Extremely exciting. Our program, the J-58, the RL-10, all the way down through the trenches, everybody was turned on. So that's the 60s. The 70s, I would put in, there 2 things happened. One, we won the big one. All of a sudden, man, we have the F-100 program, and we've got to produce, because our engine is in every leading fighter in the United States. The supremacy of the skies rests on, from a propulsion standpoint, rests on these kids. We got to make it happen. So I would say the 70s was make or break us as a division. Became a division in 1976. And we did it, not without a lot of trouble, not without a lot of setback. I always felt that place out there performed best under pressure. Now, I know all the program management theories that you shouldn't ever get into that situation. Well, that's the way the world is, you do. But I've never seen a team produce under pressure the way that bunch did. On the F-100, on the F-119 later, you could see it. We were at our best under those circumstances. Well, that was the 70s. The 80s, the great engine war. All of a sudden, brought this lion into the tent. And in the eyes of our customer, our tent was too small. And so he decided, and it's his right to do so, we should have an engine competition. But the 80s was the great engine war, which consumed us too. And then for now, the 90s is the 119. And the legacy that will give as we move into the fighters of the future. Thank God we're in the two that are on the boards now, the F-22 and the JSF. So our challenge, our legacy, if you will, is how to win the next
40 years.
I wish I was starting all over because it's, I think it's rewarding to see technology that the jet era, which is about 50 years old now, in my opinion, is only about halfway through its life. And all the things that we did and accomplished were due to one thing, our people. Sounds corny, but it's true. Without them, we'd had nothing.
42 years have been very quick, and it seemed like just yesterday I started. If I had to do it all over again, I wouldn't change a thing.
It was a very happy time. It was a time when people loved to come to work. They were so devoted to making equipment work. They would spend all kinds of extra hours at it. And it's hard to explain. People felt everybody was just very happy with the job.
And then to win, when John Balaguer said in April of 1991, April 23rd, that Dale Stick and Infantry, that we had won. The ATF program was very exciting. Everybody was in tears, hugging each other and having a great time. And then when we saw the final airplane, which is our production model, fly just last year out of Marietta, we were all thrilled and proud. And everybody at Pratt & Whitney has the right to be proud of doing a great job and making our country have air dominance for all our grandkids in the future.
Well, the world has changed irrevocably in these 4 decades. Some things seem strangely familiar. Again, we held our breath as a national hero, 77-year-old John Glenn, blasted into space. This time, aboard the Pratt & Whitney-powered space shuttle. Pratt & Whitney's Florida facility is perhaps a little less remote now. But the challenges are as exciting, as demanding as they were 40 years ago. And the promises for the future are even more inspiring. This fighter pilots call it the sound of freedom. It echoes all we have been, all we are, all we will be. It's the sound of pride, hope, and glory. Years, that thunder in the sun has been our daily declaration of triumph.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.